Okay, in this video we are going to look into building a LoRa repeater. Now LoRa is long-range radio platform which uses spread spectral modulation. Now I already built a LoRa repeater using an Arduino Nano, but the Arduino Nano only has one serial port, which made code development a little bit difficult. So I swapped out the hardware for a Propeller microcontroller, which you can see on my breadboard. Now this is the minimum part circuit to run the Propeller microcontroller, and this is the microcontroller here. Comes in a 40-pin DIP package. This is the P8X32A-D40. Now inside this microcontroller, there's 8 32-bit microcontrollers where you could run 8 tasks independently. So it's a multi-core microcontroller. Now this is my crystal. It's a 5 megahertz crystal, and inside the microcontroller there's a phase lock loop that multiplies it up to 80 megahertz. Now this is my my programming memory. This is a 24LC256 EEPROM. It's a serial EEPROM, and on boot up, the contents of this serial EEPROM is loaded into RAM of the microcontroller and run. Now this is my reset switch, which resets my microcontroller. It's a push button switch. And this is my FTDI module, my USB to serial, where I upload code into the microcontroller. Now all the parts that you see on the breadboard, you could get in a 40-pin DIP module. It's called a Flip, and it's made by Parallax. Okay, so this is the Parallax Flip. It's a 40-pin DIP module, and this has all the parts that I had on my breadboard mounted in this module. If you look on the back, we can see all the parts, and this is our microcontroller, and this is our FTDI module, and this is our USB connector. We have a reset switch on the very left. We have a power LED that comes on indicating we have power. So we could power it through the USB port, or we could power it through the input pin 5 to 9 volts, which you can see right here. And the switching power supply will output 3.3 volts at 1.8 amps, and it's short circuit proof. So everything is labeled on the front. Is our reset pin. We have our 3.3 volts output, a USB 5 volt output. So everything is labeled, and we have a TX and RX LEDs. I don't know if you can see them there. I'll hit some. You can see them flashing there. And we have our power LED, and we have 2 user LEDs on pins 26 and pins 27. So this is the module I'm going to use in my LoRa repeater. Okay, here's my LoRa radio link. So I have a LoRa module mounted on each breadboard. You can see the LoRa modules here. Now they're made by Ebyte. It's their LoRa E32 series, and the part number is 915T30D. So they're 915 megahertz modules with a 1 watt RF output. Now they run on 5 volts. Here's my 5 volt regulator, which powers the module. I have a DIP switch which puts the module into 4 different modes. So there's a normal mode and there's a programming mode where we actually could program the configuration of the module. I have an FTDI module, a USB to serial, where I could input data into the UART of the module to be transmitted or to program the module itself. And we're using a 3.3 output of the module, of the FTDI module, to power the UART pins on the LoRa module. Now we could get these LoRa modules in an extruded aluminum package made by Ebyte, and it's the E32-DTU. Okay, here's my E32-DTU, which we have a LoRa module in 915T30D inside the aluminum enclosure. And you can see it has a mounting bracket with mounting holes. That's pretty handy. And on one side we have the antenna connector, the SMA, and we have our mode switch, so we could select either normal mode or programming mode. And we got a barrel connector input, power input, that will accept 8 to 28 volts. And we could plug it in our wall wart into there, so we could power it up. And we have 3 indicator LEDs. We got power, we got TX and RX, and we can access into the RS-232 port through this DB9 connector. Now we need a cable like this, USB to DB9. This is a true RS-232 output. So we need a cable like that to actually communicate with the LoRa module. We could also communicate it through the RS-45 port, so your A and B, and we have a ground in VCC, and we could plug in a Molex connector like that, and then hook up our wires. So usually when I'm working on the bench, I use my wall wart, and I power it up through the 8 volts to 28 volts supply, and then I gain access to the RS-232 port with my cable. Now when I mount this up on a pole, then I would use the RS-45 connector, and I would power it up with the ground and VCC, so we could run this a long distance because it's a 485. It has very good noise immunity. So we can mount this up on a pole or a tower. We could run our data lines, the 45 lines up and our power lines up, and we can communicate with the module. So it's very handy to have it in an enclosure like this, so we can mount this into an NEMA-4 enclosure and mount it on our tower or mount it on a pole. Okay, this is my LoRa repeater setup. So on the very left I have my base station, which will be connected up to my laptop, and that will be receiving all the sensor data sent from the field. Now this LoRa module here would be out in the field sending sensor data to the base station. Now under ideal conditions we could get 8 kilometers between the two. That's if we have a visual line of sight between the two and a radio line of sight, which includes clear Fresnel zones. And that usually doesn't happen in the real world. So we need a repeater in the middle to repeat the data from the field to the base station. So we could set up all the LoRa modules in the field in fixed mode. So every packet that's sent will have an address and channel on the first 3 bytes of the packet, and that will point to the repeater. So all the sensors out in the field will point to the repeater, and the repeater will store and forward those packets to the base station. And all that is done using the Parallax Flip. Okay, here's our basic repeater setup. So we can see our LoRa base station over here, and all our sensors out in the field trying to send sensor data to the base station, but it can't because of this big hill or mountain that's in the way. So on top of the hill or mountain we apply the repeater. So now all the LoRa modules in the field are pointing to the repeater, and all the data will be sent up the repeater, stored and forwarded, and sent back down to the base station where they'll be received. Okay, here's my Propeller Flip that I'm using for my repeater. And you can see there the chip. It has 8 32-bit microcontrollers, and they're labeled 0 to 7, and they're called cogs, similar to a gear in a machine. So in cog number 2, I actually have my LoRa module connected through the RS-232 port into cog number 2, and it's taking data from the field and it's storing it and forwarding it and sending it back to the base. So I have it running on cog 2, and I can actually add another one on cog 3, 4, 5, so I could have multiple LoRa modules, so I could have like a concentrator, but in this case I'm just going to have one. Now my laptop is connected to cog number 1, and I could actually monitor what's going on in cog number 2. I could actually see the data flowing in and out of the LoRa module, and I could actually write code and stop this cog from running and change code on the fly. So cog number 0 is where my interpreter and compiler live, and cog number 1 is my RS-232 port to my laptop. So I actually use this for writing code. So as I'm writing code, actually all my repeaters will be working in real time, and I can monitor all of them, and I could actually change any of the code on the fly. So this is a good example where you could change hardware to make code a lot simpler. Okay, so that was a little insight on my LoRa repeater project that I'm working on. So it shows you that a repeater is one option you could use to get your data from the field back to your base station.